Hi, I'm Herb Gross, and welcome to lecture number 35 in our series of Gateways to Algebra, where today we're going to talk about solving equations through graphing. And it's actually going to be a two-part lecture. What we're going to talk about today is the general idea, and in the next lecture we're going to apply it to graphical solutions of quadratic equations. Now, basically what the idea is that, remember what we said before, every time you multiply by the input, the degree of the polynomial equation is going to increase by 1. So let's just take a problem like this. Let's suppose I took the graph y equals x cubed plus x. Where might that come from? It would come from what? Start with x, multiply by x, add 1, multiply by x, and the answer is y. So let's check that out. If I start with x, I multiply by x, that gives me x squared. I add 1, that gives me x squared plus 1. And I multiply by x. Well, the x squared becomes x cubed, and the 1 becomes x. So I now have y equals x cubed plus x. Now watch how easy it is to start with x and go to y. I say, well, what if x was 2? If x was 2, I start with 2, multiply by x, 2 times 2 is 4, add 1 is 5, multiply by x, 5 times 2 is 10, so the output would be 10. Suppose I said, well, what if the input was 1? I'll start with 1. Multiply 1 by 1 would give me 1. Add 1 would give me 2. Multiply by x, which in this case is 1. So 2 times 1 is still 2. So the answer here would be 2. So in other words, if x is 1, the y value will be 2. And by the way, graphically, that's very easy to graph. In other words, what you say is, what does that tell me? It says when x is 1, y is 2. What does this tell me? It says when x is 2, y is 10. Where would the algebra come in here? Well, for example, suppose I say, I wonder what value of x I should pick if I want the answer to be 4. Well, you see what the problem now is? See, I want to solve the equation x cubed plus x equals 4. I know that 1 is too small. I know that 2 is too big. I know there's going to be an answer between 1 and 2. But how can I reverse the steps over here? See, to get past this step over here, I would have to undo multiplying by x. That means I would have to divide by x, but I don't know what x is. So let me show you what the graphing method does over here. See, I want to try to solve the equation x cubed plus x equals 4. What I'm going to do instead is I am just going to graph y equals x cubed plus x. You see, once I have the output, it's very difficult to find the input. Let me do the easy thing. Let me start with the input and find the output. For example, when x is 0, 0 to the third power plus 0 is still 0. So when x is 0, y is 0. When x is 1, we've already found out that y is 2. When x is 2, we've already found out that y is 10. And by the way, could I take other numbers and work this out on my calculator? For example, what would I do when x was a half? See, if x was a half, what would happen over here? A half to the third power is 1/8. 1/8 plus a half is 1/8 plus 4/8 is 5/8. So I could do what? I could plot the point 1/2 comma 5/8. And could I then get a whole bunch of points like this? And once I have a whole bunch of points like this, could I take a chance and assume how they're going to be joined? So now, for example, I want to solve the problem x cubed plus x equals 4. See, what I've done here is I've drawn the curve y equals x to the third plus x. The easy way to handle this from an arithmetic point of view is when you start with the x value and you want to find the y value. All this is asking me to do, when I have x, let me write it big so you can see what I'm saying, when x cubed plus x equals 4, what this is saying is what? I want the output to be 4. So come up here. See, there's where the output is 4. Draw a horizontal line. See, what's the name of that line? If I draw it right, what's the name of that line? That line is called y equals 4, because every point on this line has its y coordinate equal to 4. See, then what I do is, I know what? The point I'm looking for has to be on the curve y equals x cubed plus x. It also has to be on the line y equals 4. You see, where these two meet, the y coordinate is going to be 4. I'm looking for the x coordinate. So all I have to do now is project down here, and see what the answer comes out to be, and it looks to me like it's going to be about 1.4. You get the idea? I take the 4, come across, come down, it projects to be about 1.4. I don't know exactly the right answer, but what can I do now? If I'm right, what should happen? If I replace x by 1.4, then x cubed plus x should come out to be 4. So now with my calculator, can I take this guess? If I take 1.4, I'm going to take what? 1.4 to the third power. Okay. Now how would I do this on my calculator? I enter 1.4, I hit the y to the x key, enter the 3, hit the equal sign, hit the plus sign, enter 1.4, hit the equal sign, and I get what? 4.144. Not bad, but I guess what? A little bit big. Evidently, the answer should be smaller than 1.4. Well, why try 1.39? I'll just make a little bit bigger jump and see what's happening here. I'll try 1.37. I enter 1.37, press my y to the x key, enter the 3, the equal sign, the plus, 1.37, the equal sign. Now I get what? 3.941. Remember what I'm looking for? I want the output to be 4. So 1.37 is still too small, isn't it? Let me try 1.38. Do the same thing again. If x is 1.38, 1.38 to the third power plus 1.38 turns out to be 4.008072. That's a real nice approximation, just a little tiny bit too big, isn't it? So I'll try something a little smaller. See, 1.379. I'll raise that to the third power, add 1.379 to it. Now I wind up with 4.00136, etc. Am I really zeroing in over here? In other words, do you understand that once I have a good idea of what the answer is, I can make better and better approximations. As you learn more and more sophistication, we also, that means what? More advanced material. We find faster ways of making that approximation. See, in graduate school, we have a whole course called numerical analysis where we do things like that. But did you see what I'm saying? To get a hint as to where the answer was, look how much easier it was to draw the graph. Because for the graph, you can start with the input, the x value, and solve for the y value. Once you've located enough points, you know what the curve looks like. Once you know what the curve looks like, starting with the y value that you want, you can project over to the curve and come down and approximate the x value. The problem with that method, of course, is that the diagram, the solution that you get, will never be any more accurate than the picture that you've drawn. So, and I don't know how can you ever draw a picture by hand that will measure to 5 decimal place accuracy or things like this. Though we do have computer drawings that will do things like that. But let's not worry about that right now. I just want to see if you get the hang of what we're doing this way. So another way, by the way, another way of doing this is when you want to solve, see, a lot of people prefer, instead of looking to see where a particular horizontal line cuts the curve, most people would like to identify the solution of an equation with where the curve crosses the x-axis. Now, what characterizes the x-axis? The x-axis is characterized by the fact that what? Every point on the x-axis has its y-coordinate equal to 0. So another strategy for doing this is, given the equation x cubed plus x equals 4, what we do is we again make the right-hand side equal to 0. That gives us what? X cubed plus x minus 4. See, we subtract 4 from both sides equals 0. Okay? Now you see what happens is, this says what? This is where the curve y equals x cubed plus x minus 4 has its y coordinate equal to 0, meaning it crosses the x-axis. So in other words, what we're saying is the roots of the, it doesn't have to be x cubed plus x minus 4, that's the function. Any function of x equal to 0, what we're saying is the roots of the equation f of x equals 0 are the x-intercepts of where the graph y equals f of x crosses the x-axis. You see, the problem with trying to solve this equation is you're being forced to find an input that matches this output. The beauty of plotting this curve is you can start with the input, find the output, and all you're going to do is, once the curve is drawn, you are going to find out where that cuts the axis. By the way, we'll talk about this more later, but can you visualize a connection between this function and this function over here? We just drew this function over here. Knowing this, do you think there's a way of drawing this one kind of easily? Do you see what this thing says? This says that for any input here, if you put the same input over here, the output's going to be what? 4 less, because this is x cubed plus x. This is 4 less than x cubed plus x. And what that says is this is going to be the curve y equals x cubed plus x, pulled down by 4 units. So these are just things that you might be interested in knowing. So let me illustrate this in terms of a problem that I'm sure you can already do. In fact, if we can't do this one, then it's really back to the drawing board. Suppose I say to you, solve the equation 2x minus 7 equals 0. Hopefully this reminds you of way back early in the course. What's the strategy? Get the x's on one side, the numbers on the other. So to get rid of the 7 over here, since it's being subtracted, we're going to add it. If we add 7 to one side, we have to add 7 to the other side. We wind up with 2x equals 7. To find x by itself, we divide both sides by 2. So x is going to be 7 over 2, or 3.5. Certainly a baby type of question. But what I wanted you to see is, if I didn't know any algebra at all, but knew how to read formulas, could I draw this graph? Y equals 2x minus 7. Sure. In fact, one way of remembering this is what? It's a graph where the x-intercept, where the slope is 2 and the y-intercept is negative 7. We could draw that. By the way, you don't have to do it that way. We know, for example, when x is 4, 2x minus 7, that would be 2 times 4, which is 8, minus 7 is 1. So 4 comma 1 is a point on this line. And when x is 5, 2 times 5 is 10, minus 7 is 3. So 5 comma 3 is going to be a point on this line. So what will this line look like? It's the straight line that joins 4 comma 1 to 5 comma 3. Okay? Now that we've drawn this, how do we solve the equation 2x minus 7 equals 0? Look at this and look at this. Isn't this the special case of this when y equals 0? What this says is, for what value of x will y equal 0? Well, whatever that value of x is, that's going to be the x-intercept. See, y is 0 when you're on the x-axis. So we draw this line, and all we have to do is what? Look to see where that line crosses the x-axis. And is it pretty clear that that's 3.5? Isn't that the same solution we got algebraically? See, again, the real thing to be careful about is this looks like 3.5, happens to be the right answer because this was a simple problem. But in a more complicated problem, how do we know this wasn't 3.49 or 3.50123? You see, the graph will give you a certain amount of accuracy, but you still want to be able to fine-tune this thing using the mathematical analysis, okay? So let's just take a little break and make sure that you grasp this particular concept. In other words, to solve an algebraic equation, when all the variables are on one side, write the equation in the form something equals 0. Then take the left-hand side, set that equal to y, and draw that graph. And wherever that graph crosses the x-axis, that will name a root of your equation. For example, suppose this is the curve y equals f of x. Suppose this is the curve y equals f of x. I'm even going to tell you what the rule is. This is the curve y equals f of x. And I want to solve the equation f of x equals 0. See, in other words, what value of x will make the output 0? The first thing you're going to say to me is, how do I know? I don't know what f stands for. Yes, you do. See, because I've already implicitly, by this graph, I have implicitly defined a function for you. Why? Suppose you say, let's suppose this number over here is 3. You say, I wonder what f of 3 is. In terms of the graph, all you're going to do is what? Go up to here, come across to here, and whatever this number here is, that's what f of 3 will be. See, the graph says what? Given the input, this is the output. Now, what we're saying is, when will the output be 0? The output is 0. See, it's measured vertically. The output is 0 when you're in the x-axis. Where are you in the x-axis here? Here and here. So whatever numbers represent these 2 points, that will be the solution of your equation. In other words, if you plug x1 into the program, f of x1 should turn out to be 0. If you plug x2 into the program, f of x2 should turn out to be 0. Now, of course, if it doesn't work exactly, it means that the thickness of the dots here had some bearing on what you were doing. See, let me see if you can, I don't know if I drew this easy enough for you to read. I can't even read it myself half the time. I think I'm going to put my glasses on while I look at this, and I'll mark this up better so you can see what this is. I've labeled this point over here negative 3.1, comma 0. This point over here is labeled negative 1, comma 0. This point over here is labeled 3, comma 0. And this point over here is labeled 5.8, comma 0. Okay? This point, this point, this point, and this point. And what the question is saying to you is, based on this being the graph y equals f of x, what are the roots of the equation f of x equals 0? Now again, see, equate these two together. This says 0 equals f of x. Put these two together. Isn't this just saying, for what value of x will y be 0? Y is 0 whenever you're on the x-axis. Where does this curve cross the x-axis? It crosses the x-axis when x is negative 3.1, when x is negative 1, when x is 3, and when x is 5.8. So the solutions of this particular equation, based on the graph, would be negative 3.1, negative 1, 3, and 5.8. Okay? And by the way, notice what happens here. See the shape of the curve here? Can you see what's going to happen? When this line gets up here, okay, and this line goes up here, you see what's going to happen? If I pick a value of x, a value of y other than 0, can you see that this curve stays the same, but how many times that horizontal line cuts the curve is going to depend where I draw that horizontal line. Or what if I drew a vertical line like this, you see, or a line that was slanted like this? Geometrically, the picture will tell me roughly how many answers I should expect to find. And what this involves is that sometimes you want to shift and raise a curve. And I thought that one thing I'd like to show you is what happens over here. So what I'm going to do is, in a single diagram, I'm going to draw 3 curves for you. They're very simple curves. The first one is going to be y equals 2x. Now, we can do that almost by sight. See, when x is 0, y is 0, and the slope is 2, that means every time you go 1 to the right, you go 2 up. That line is going to look like this. Okay? And by the way, as I'm calling this 2x, you can really be thinking of 2x standing for any function of x. Now what I want to do is to see what happens if I just add 3 on to the 2x. In other words, it doesn't even have to be 3. It could have been 5 or 7. What would happen if I added the constant onto f of x? And the other thing I want to see is, what if I added the constant to the input rather than to the output? See, suppose I did this. These are two very important things to keep in mind. So to see what's happening, let's see if we can predict what's going to happen first. Suppose I put any value of x in here. Suppose I put x equals 5 in here. If x equals 5, 2x is going to be 10, isn't it? What will 2x plus 3 be? It will be 13. Is it a coincidence that this is 3 more than this? No, because this function here says what? Take the answer you got here and add 3 onto it. In other words, what do you think the graph of y equals 2x plus 3 is going to look like? It's going to look exactly like the graph y equals 2x, only it's going to be what? 3 units above it. See, what you're going to say is, whatever the output would have been before, you're going to be doing what now? Adding 3 onto it. So you're raising that line by 3 units. What happens over here? See, here, when you put x equals 0, the fact that 3 is being added onto it says what? Instead of getting the output that corresponds to x equals 0, when x is 0, you're going to get the output that corresponded to what? 3 over here. In other words, this is going to shift horizontally this graph by 3 units. So I thought that if we just drew this, you would get an idea of what's happening over here. See, the middle line is y equals, I'm sorry, the black line is y equals 2x. Now what happens if I graph y equals 2x plus 3? It means I just add 3 onto the output. No matter what the output was, I'm going to add 3 onto it here, 3 onto it here, 3 onto it here, etc. What's happening over here? I'm going to get the same line displaced by 3 vertical units. Now, what happens on this line over here? the line that says y equals twice x plus 3. See, if I put in x equals 0 here, when I put in x equals 0, it's going to give me what? X plus 3 is going to be 3, and twice 3 is going to project up to the 6 over here. See, but the problem is this output was obtained for the input 0, so that 6 really has to come to where the 0 is, and what that's going to do is what? It's going to shift this curve 3 units in this direction. You see, the point I'm driving at is that when you're studying solutions of curves, solutions of functions, raising or lowering this will change the number of solutions. In other words, I just want you to get an idea of this. Suppose this is the curve y equals f of x. And I say, how many solutions does the equation f of x equals 0 have? How many solutions will it have? This crosses the axis in 3 places, doesn't it? So f of x will have f of x equals 0 has 3 solutions. Suppose I say, suppose this point over here is x equals, suppose this is the line y equals 4. How many solutions will there be to the equation f of x equals 4? Well, how many times does this line y equals 4 meet this curve? It meets it once over here, and it meets it once over here, so there's only going to be what now? 2 solutions. See, notice that raising the line is the same as lowering the curve. You see, how many solutions this shaped curve is going to have will depend on where we draw the x-axis. See, suppose we drew the axis up here. How many times does this curve now intersect this axis? All these other points down here are where? They're below this x-axis. The only place that the intersection is going to take place is over here. So if we were to take this curve, you see, and lower it so that the x-axis came over here, there'd only be one solution. Well, the point that I'm driving at is that graphing is a terrific way of being able to analyze solutions to equations, being able to analyze what kind of changes you can make that will dramatically change the solutions to the equation, and once you have the solution to the equation geometrically, how to refine it to be a better algebraic solution. And we're going to stop over here, because I just want you to get the idea of what graphing is all about, graphical solutions. And what's the key point? To solve an, if the f of x equals 0 bothers you, let me just put some concrete functions in here. Suppose I wanted you to solve the equation x cubed plus x plus 7 equals 0. All we're saying is what? Draw the graph y equals x cubed plus x plus 7 and see where that graph crosses the x-axis, and that will give you the solution. What I want to do next time is apply this philosophy and conversation specifically to how we get the graphical solution of a quadratic equation. So until next time, as I say, study hard, have fun, stay young. See you soon.